In this short lecture, I will give a brief introduction to the theory of cross-product algebras. Let capital F be our base field, and let's consider a Galois field extension of degree n, and let's write G for the associated Galois group of this field extension. Let's also consider a normalized Tuchel cycle. And by this, I mean the following: a map from G cross G to the invertible elements of capital K, which satisfies the following properties. So sigma of C tau gamma times C sigma tau gamma is equal to C sigma tau gamma times C sigma tau, and this for all sigma tau and gamma elements of G. So this is what it means to be a Tuchel cycle, and normalized in the sense that C, the value of C at 1 sigma is equal to C sigma 1. It's equal to 1 for all elements of G. So given this data, we can consider an associated cross-product algebra. So cross-product algebra. They were introduced by Noether around 1930s, and they are defined as follows. So we have our Galois field extension, our Galois group, and also this normalized Tuchel cycle. So we consider a vector space where we take the sum indexed over all elements of the Galois group and then copies of K, capital K, and then formal symbols nu sigma. So it is a n-dimensional capital K vector space with bases are given by these formal elements indexed by sigma elements of the Galois group. So on this vector space, we can introduce a multiplication and to do this, we just need to impose certain relations. So first of all, how do we multiply these two generators? So by definition, we just take nu of sigma tau. So this for all elements sigma and tau of the Galois group. But then we still use the Tuchel cycle here. So we take the Tuchel cycle sigma tau. And the other issue is that when you multiply on the left by an element of capital K and an element sigma of your Galois group, you can move your lambda to the right. But when you do this, you need to act using the element of the Galois group on lambda. So these are the two relations. Using these two relations and distributivity, we end up with a multiplication, a well-defined multiplication on this vector space. And this is how the cross-product algebra is defined. So an important remark about the cross-product algebra is that it is a n-square dimensional F algebra. So note that it's not a K algebra. And the reason for this, it is precisely the relations that we are imposing in order to define the multiplication. Okay, so what's so interesting about this algebra is that, let's see an example, is that it actually generalizes the construction of cyclic algebras. So let's assume that that our Galois field extension is actually cyclic. And moreover, let us choose a generator, so an element of G, which is a generator, and also an invertible element on, an invertible element of F. Then, given this data, what can we do? We can consider the following Tuchel cycle, normalized Tuchel cycle, with values here on the invertible elements of capital K, which is defined as follows. So we take sigma I, sigma j, and so this element here, it is sent to 1 if the sum of I and j, it is strictly less than n, and to this element beta if the sum of I and j is greater or equal than n. And this for every, so the n and the j, they are varying between 0, 1, 2, etc. until n minus 1. So we end up with this normalized Tuchel cycle. And the observation here, it's a simple verification that if you take this cross product algebra with respect to this Tuchel cycle, it is isomorphic to the cyclic algebra, where here you have this specific generator and this element beta. So here it's your cyclic algebra. So it turns out that this construction is pretty general. It generalizes cyclic algebras. Let's see one important feature of cross-product algebras. So it's another interesting remark. Suppose that we have two normalized Tuchel cycles. So they are, both of them, they are normalized Tuchel cycles. And so one may wonder, when are those cross-product algebras associated to these Tuchel cycles isomorphic? So we can consider this one, or we can change the Tuchel cycle. And it turns out that they are isomorphic if and only if, so this can be explicitly described, if and only if there exists a function from G to the invertible elements of capital K, such that the following equality holds. So such that when you take C sigma tau multiplied by C prime sigma tau inverse, that is equal to sigma applied to the F tau, and then F applied to sigma tau inverse, and then to the value of F at sigma. And this for all sigma and tau elements of G. So we have this description of when two cross-product algebras are isomorphic when we vary this normalized Tuchel cycle. Well, the most important fact about these algebras is the following, is that all of them are, in fact, central simple algebras. So they are so general that one may wonder, is a general central simple algebra a cross-product algebra? And the answer is yes and no, in the following sense. So every central simple F algebra is isomorphic to a cross product F algebra. Well, this remark, it's not true, it's false. And the reason is precisely this word here, isomorphic. It doesn't work like this. It's not true that every central simple algebra, it's actually a cross-product algebra, but it's not very far from this. So one needs to replace this word isomorphic by a weaker notion of isomorphism. So if you want to learn which word one should place here, stay tuned for the next lecture.